Okay. And I will start with the first presentation. Dr. Kaya will present this presentation called Investigation the Solidification Temperature of High-Strength Low-Alloy Steels using the Shell Solidification Model with Calfett methodology. Yes, Mr. Kaya.
Hello to everyone. I'm Adem Kayadaran. With permission of the Professor Gün, today I will conduct you a presentation. My presentation's topic is investigating the solidification temperature range of HSLA steel using the Shell solidification model with Kalpat methodology. Before I start, I condemn terrorist attack to the TUSAŞ campus in Kazan. I remember with my best regards to the martyrs. This is the general presentation overview. First, I will give some information about my presentation. Second, I mention about Shell solidification, Kalpat methodology, and thermocalc. There are general information about materials, Shell and calculation scenario on the pipeline. In result, I will have been conduct you the conclusions. Solidification plays a crucial role in various manufacturing techniques, including casting, welding, and additive manufacturing. Shell solidification is a model that describes the solidification of binary alloy, assuming complete mixing of the liquid phase and no diffusion in the solid phase. Originally conceptualized by Gulliver in 1913, the Shell-Gulliver model provides a theoretical framework for understanding the redistribution of solids during the solidification process. Kalpat is a computational method for predicting thermodynamics properties of materials, such as phase diagrams, thermodynamic data, and phase transformations since 1970. In this study, thermocalc 2024B version was used. The TCFE13 database defined for steel materials was utilized alongside the MOB FE8 database, which is used for mobility calculations. And thermocalc is a commercial software package that uses the Kalpat method to calculate thermodynamic properties of materials. Chemical specifications of chosen material can be seen in table. I use 3 HSLA, high strength, low alloy steels used. These values enter to the system definer modules in thermocalc. You can enter your chemical composition to the thermocalc system definer module. There are 4 Shell solidification models in thermocalc, which based on Kalpat methodology. The first model is based on the classic Shell-Gulliver model. The second model allows for the assumption that one or more alloying elements rapidly diffuse, depending on the station. The third model is known as the back diffusion in the primary phase model, with thermocalc providing satisfactory results for all 3 of these models. A fourth model incorporates solid trapping in the primary phase for calculations involving high Saltification rates. We use this model especially in additive manufacturing techniques. Since the solid trapping in the primary phase, the model name is solid trapping in the primary phase. Model requires a number of special definitions within itself. Calculations were made only with the first three models in the study. Three different calculation methods were employed. The first model assumes carbon as the only phase diffuser. The second model assumes all alloying elements as phase diffusers. And the third is the Scheil with back diffusion model where carbon is set as the phase diffuser. The Scheil with back diffusion model is the most advanced Scheil model available in thermocalc. And it provides the most accurate results for steel materials. As seen in previous table, three high-strength low-alloy steels are chosen, each steel employed with three Scheil model. You can see in table now. First one is only carbon phase diffuser. Second one is all alloy element are phase diffuser, and the third one is back diffusion calculation with primary phase. In this model, cooling rate is 15 Kelvin divided second, and the primary phase arrange automatic. The results of three different scenarios for selected steels are shown in the figures. This is for ER70 S hyphen A1 steel. For ER19, in the calculation where only carbon is a phase diffuser, the calculation ends at 98.8% qualification. This is assumed to be a calculation error, and it is thought that the temperature will drop below 1439 Celsius degree when the calculation approaches the 100% solidification limit. This is for ER 110. In picture left that I mentioned situation. The results will be analyzed in a table. This is the results table. These results are detailed in table since the carbon atoms can diffuse rapidly due to their size. The solidification range in case 1, case 1 is only carbon is phase diffuser, is expected to be higher than the solidification range in case 2 for all steels. As a matter of fact, thermal calculation results confirm this. For all three steels, the solidification interval calculated in scenario 1 and scenario 3 is similar. Scenario 1 case 1, scenario 3 case 3. While in scenario or case 2, the solidification interval is smaller than the other two scenarios. Only for ER90, a small calculation error was observed in scenario 1. This was explained in detail above. For further reading, I think the conference published book will be published after conference. You can read it from conference publish. Thanks for your listening. If you have any questions, I can you. Thank you. Thank you.
Thank you, Mr. Kaydala. And the second one is Dr. Halmeyer here? Halmeyer? Yeah. Dr. Halmeyer will present his study called zinc forms made by a cold sintering process.
Yes. Thank you, Chairman, for letting me present our latest work on the manufacturing of zinc foams by a cold sintering process. Everyone who heard about powder metallurgy knows what sintering is. So it's a very simple thing. We heat the sample or the part in order to make metallurgical bonds between the particles involved. If these particles are not bonded metallurgically, their mechanical properties are almost inexistent. So, for the beginning of the powder metallurgy, this sintering was done by using heat to improve the diffusion of atoms from the mostly the particle surface to the sintering neck. It's very nice, very well working, but you need high temperatures. High temperature will see about 0.7, 0.8 from the melting point of the main component. Since the middle of the last century, NASA scientists were trying to get a different approach to transport the materials from the particle into the sintering neck. They tried everything and found in the last years that about 100 materials, mostly oxides, but all of them ceramics, can be sintered using a chemical or electrochemical method. They said it's called cold or chemical sintering. Depending on which group you ask, they said cold or chemical. This
without any heat, right?
Yes, without, well, there is some heat, but a lot less than in the classical system. This is based on a solution precipitation mechanism to transport the materials from the particle to the sintering neck. In order to have this solution, you need some liquid. To enhance this dissolution process, you need to apply pressure. Until now, it's okay, simple. Well, not so simple. For those 100 ceramic materials, things are okay. But for metals, in order to enhance this dissolution, you need pressures that are impossible to obtain in industrial way. Not in a convenient way, but in theory, you can make some tens or hundreds of gigapascal, but for a practical application, there's no sense. So, some breakthrough occurred some years ago when some groups found a way to chemically sinter zinc nanoparticles. They use it to a complete different approach. They are sintered some nanoparticles that are inside some conductive inks. The idea is okay, but with this, what the solutions proposed by them, it is impossible to make 3D parts. B-dimensional parts is okay, you can do everything you want, but to construct a three-dimensional usable part, it's a problem. The second article here, interesting article. They managed to obtain three-dimensional parts, but in order to have good electrodes for zinc air batteries, you need high porosity. They used a slurry method. They mixed the powder with some liquid and sintering them. You have a porosity of about 20%. That's not really a porous material. So, except from these groups, I couldn't find anything that on the internet that says cold sintering and metal. Because those old people from NASA say that's impossible, and probably they were almost right. So we make the goal for ourselves objective to make some porous zinc material using a combined powder metallurgy and cold sintering process. What was our idea? Based on the previous works, of course, and our expertise in making metallic foams by powder metallurgy. In order to make porous materials, the simplest way with powder metallurgy is to use space solder. We mix the powder and the space solder, extremely fine powder. And as you know, having a small particle size, it means you have problem with surface oxide and surface hydroxide. And most particles sintered hard in this case. But in our case, we use that surface oxide, zinc oxide, no? Zinc oxide, it can be easily sintered, cold sintered. So we use that surface oxide to sinter the particle together. So we added the acetic acid and applied some pressure, and after successful or less successful attempt, we have a good or bad metallic foam. Yes, of course, the leaching part. So what were we doing exactly? So we make some spherical zinc powders with a low particle size, 1 to 10 microns. We choose spherical particles, but they are easier to measure the sintering degree. And some bigger polygonal shape salt particle. We mix them together and we made 4 types of samples. One type with 40% porosity, 40% salt particles, another with 60% salt particles, and from both porosities, we made with a smaller and a bigger particle size to see how it's dissolved during the dissolution process. We poured this particle blend in a dye, added a few drops of liquid containing acetic acid, water, and ethanol, tested, heated to the decomposition temperature of the zinc acetate, that's around 250, and to a higher temperature, 300, where the acetic acid is not stable anymore. So, our chairman asked a question before. This is heat. What? Cold sintering, it's considered if the temperature used is less than 250 degrees. So, after the pressing and holding the temperature to 30 seconds, took out the sample, leave it 1 day to finalize the evaporation, and after that, another day in flowing water to dissolve the salt particles. The samples became manageable. You can hold it, you can throw it to the wall, you can drop it, nothing bad happens. So first things first, it seems okay. So we obtained porosities a little lower and higher because although we homogenized and calculated everything right, because the density of the salt and the zinc is very different, almost 2 degrees and 7 degrees. When we manipulated the powder mixture after the homogenization, there was some separation. Also, in the porous walls, there are some inherent porosities that's given by the powder packing. So we had porosities close to the desired one. These variations are specific for this method, so nothing really here. Here I presented the left is a sample with just after the cold sintering process. The rectangular shape is the salt, the other are the zinc particles. Well, we cannot see these particles. The middle one is after the removal of the salt at a lower magnification, and the last one is an image presenting the pore walls. We can see that links sintering between the particles are there. It's okay. And from these images of the pores wall, we measured the sintering degree as a ratio between the sintering neck and the particle's diameter, considering similar sized particles. So in both cases, for all pore samples, we saw some images. There are some sintering there, some things that might be some sulfur oxides. We'll talk about a little later. So for all samples, we have sintering degree over 60%, 60.6. That means excellent. No, for filters, they can do a very good job with 0.3. We are double, we are an excellent sintering. Independent of the temperature used. Okay, what's inside? We started from a powder, zinc powder, no, that has zinc and oxide, simple. It's a little small, but you can believe me, it's there. After the cold sintering, when we didn't heat the samples, we leave them at room temperature, we see only the zinc. The zinc oxide with the acetic acid forms usually zinc acetate, which was below the limit of our experimental setup. So we couldn't see that. After heating and decomposing, after suffering the zinc acetate decomposition, it decomposed in air to zinc oxide, which is there also. If we heat it to higher temperatures, beside this decomposition, some oxidation also takes place because everything is done in air. So the zinc content, oxide content is higher. It can go up to 20%. Well, the powder, we started about 5% oxide. At 250 degrees, there will be around 10–12%, and around 20 at the highest temperature. From the point of view of compression curves, it's nothing really that seems to be an aluminum metallic foam with those nice curves. But for me, there are two good things in there. One, the compression strength, and they are 60–70%. Keeping in mind that the compression strength of zinc is around 80, the minimum, and up to 160, depending on some material factors. And we have a wide deformation range. Zinc has a hexagonal structure, which is not the best in deformation. So, putting head-to-head everything. As we see, when the sample was not heated, there are some compression strength and plateau strength that are comparable with some. Thank you. Emotions. I still cannot get rid of them. So at room temperature, the compression strength is low, but I could find a lot of metallic foams made by powder metallurgy who had lower properties. So it's not the worst. If we heat it up, where the zinc acetate decomposition, we have decent mechanical properties. With heating higher and having a higher oxide content, some fragility appears and the mechanical properties becomes a little less. Yes, they are still a work in progress. They are not everything finely polished, but the general idea is it's working. So, as the conclusion, it can be done. You can make metallic foam from cold sintering zinc particle. Yes, it's not just metal, it's some oxide, but it's okay. So, and the compressive strength, the mechanical properties are good enough to be used. The main idea behind this is zinc air batteries, so they are not needed super hyper mechanical properties. So, thank you for your attention.
Any question?
Yes, please.
So I wonder actually how we can use that parts that for synthetic technology for battery technology.
You use the porous zinc as anode,
And you put some
electrolyte, and form that's similar to lithium ion batteries, but zinc does not tend to get fires to caught fire so easily than lithium, and its theoretical properties are even better of these batteries than the lithium ion batteries.
Thank you so much.
You're welcome. Thank you.
Dr. Talmeyer, thank you for this good and interesting presentation again. And then next presentation is Dr. Ata here, is here. Sadia Ata. Neydi onun? Benim var mı? Yok. Okay. Ashok Vasista. Ashok Vasista. Dr. Abubakar. Dr. Abubakar will present this study called Research and Development of GD rope-based nuclear radiation detectors.
Okay, thank you.
Are you related with the Vincent Abubakar in our country?
I
You know
know,
Vincent
but-
Abubakar?
I know. Well, he's Cameroonian, I'm Nigerian.
Yeah.
Which one are you talking with?
Yeah, I think the research one, this one.
Okay, wait.
Ha, indirin. Ne yaptın?
Okay, first of all, I would like to thank you for giving me this opportunity to share my research. I'm Saleh Abubakar. I'm doing my postdoc at LGS University, LGS Neutron Research Group with Professor Emrah Trash. So every place I go, I need to introduce my group because we are doing interesting work here. So in our group, we have different field study professors. We have nuclear physics, solid state physics, and high energy physics. And in our group also, we have different students from different universities because our goal is to create an atmosphere that we can work with not only high energy physics or nuclear physics. We want to work with the computer scientists, which will work on the AI, deep learning, and simulation studies, both on particle detection and also nuclear radiation detectors. So you can see here in our group, we have many undergraduate students because we want to encourage them to have that good synthesis of experiment from different universities, from Gazi, from Boğaziçi University, from Otto and other places. And thanks to our professor, we have good international collaboration dealing with the high and particle physics, which is related with the sound EOS formula, which included the NOVA, which is non-off axis radiation with the particle detection, and any neutron antineutrino particle interaction, and doing which is called the underground particle detections. So mainly our group is more focusing on particle detection and high energy physics. Okay, as I mentioned before, so now what are we doing? Normally we are working on the neutron detection studies and calorimeter scintillation studies. So our aim is how can we improve this neutron detection? Normally we have like the gigantic neutron detection, and also we have Cherenkos. And also we have scintillators by dump materials, mostly gadolinium, because when you dump gadolinium on the scintillator, it's easy to get neutron capture and radiation separation or emissions. And also at the same time, we are working on the calorimeter and water-based liquid scintillation studies in our group. But the more interesting system, which is my field, we work on the silicon-based radiation detection. Normally, this silicon-based radiation detection, we are working on the high radiation detection, like gamma radiations, but we want to integrate something to make this radiation detection to be able to measure low radiations particles, such as neutron. And when we were able to measure neutron, so we can get the interaction between neutron and neutrino detections. So this is our one of our CIVITAC project. So it's already started this year. So we are working to interrogate the gadolinium dump under the gate of this material so that it will be easy for us, because as you know, gadolinium is easy to capture neutron and also emit gamma radiation. So it will increase the sensitivity of this material and also increase the neutron capture. So as I mentioned before, many of our study is space applications, medical applications, and also defense applications, because all this is related with the high radiation and high particles exposures. So now the main things in our study is like we have the main gate as yttrium oxide. So in order to start for the started point without the resistors, transistors, so we say we have to work on the capacitors, because for the capacitor you can easily assess the capacitance voltage or capacity of the charge density of the material. So we deposited different layers of gadolinium oxide above yttrium oxide gate, as you can see here. Normally in our work, same study is not related to our distance, because I just want to show like, yeah, we were able to get this material as a cross section. You can see the multiple layer of the material as the first one you see 10 nano, 100 nano gadolinium single, and also we have 500 nano gadolinium single. I couldn't put the 10 nano gadolinium because they couldn't get that image of it because it's so tiny. So after that, we study the structural property of the material. As you can see, normally the polycrystalline material, yttrium oxide, and the intensity is very high and distant. And also we take the separate excited measurement of the material for the gadolinium 100 nano degree and also gadolinium 500 nano degree and nanometer. I'm saying degree. I'm sorry for that. So we compare, as I expected, when you have the oxide material, if you deposited a metallic material, it's either to get the shift by the angles or you reduce the intensity of the material. That's what we are looking for, and we get it. Because you can see here, the intensity of single yttrium oxide, it has high intensity, but when you deposit the gadolinium oxide, here we are not working on the crystallinity or structure of the material. We just want to see how gadolinium also would affect the gate oxide material here. So you can see here, there is a angle shift and also the decreasing of intensity of the material, because gadolinium oxide is a metallic material, right? So that's why we are working on it here. For the gadolinium oxide, in sensors technology or detector technologies, sometimes low capacitance is easy to detect low radiation materials, but high capacitance, you can get a high reliability, but sensitivity is a bit low because you need more energy or more electric field or what called a bias that will trigger that material to give you a sensitivity. So here, as you can see, gadolinium oxide has high capacitance, but it's more reliable because the depletion layer started as a zero, which is looks as a what I call it as a ideal most capacitor curves. So that is what we get for the electric distance, and we are going to publish the comprehensive study about the radiation detection and other thing about this study on articles or maybe in these preceding papers. So the conclusion of this material, we were able to see that the gadolinium oxide really has a high reduction of interface between the oxide and the silicon oxide. Because as you can see here, normally if the trap oxide density of material or interface density of material is high, your distance depletion region will be above. If it's entire material, right? It will be more away from zero, right? But when we deposited the gadolinium oxide, our depletion region is closer to zero. So it will be easy for us to have the reliability of radiation detections. And our future study is easy. Like we want to make most base particle detectors, the integration of gadolinium, and we have the scintillation issue, but we want to make most base gadolinium dump particle detections, and we want to make a lot of different radiation sources to test beta, gamma, alpha, and neutron radiation sources so that we can see the differences of these materials. So we can integrate this material as a particle detection, not only radiation, high radiation detection, which low radiation materials. So I would like to thank our group is sponsored by Tubitak and other our school, what they call it, project office on this thing. Thank you for your attention. Any questions?
Thank you.
Okay, actually we have like two presentations because one is my professor going to present this. I'm going to present for him.
Yeah, you can.
Yeah.
Go ahead.
Please check out something real quick. Şu an katılmak isteyen biri yok gibi gözüküyor. Aynen. Kimse davet etmemiş. Which one?
The second one, the
This one?
development. Yeah, the
Yeah,
development.
okay.
Okay, I have already mentioned this but here I'm going to discuss about the development and performance of radiation, secondary emission radiation. Maybe as you should know, photo multiplier tubes. So here we want to interrogate normal conventional photo multiplier tubes with our own integrated cycle, so we can have secondary emission photo multipliers here. So I will just pass this one because I've already explained if there's no issues. And this is how we are doing here. So normally these secondary emission sample models, conventional PMTs, they have single electrons. when you give high energy or high voltage, if that single electron is detected, so the photosensor will not work. So our aim here is like we have secondary emission radiation. When the first divider is up, so the secondary electron will get into, so we can easily get the access of the photo detection of the photons or neutron or any other particles. Okay. So this PCB is designed in our laboratory with our engineering group and with the physics group. So we have different modes. We have second mode, first mode, and the third mode. So when the first mode is not working, the electron is divided, so the second mode will automatically get into work. Like normally we are taking particle detectors in a very secured black box, close, high radiation distance. So it will be easy for you when you have different modes that you can control it remotely. If the first mode is not working, automatically the second mode will get into work. So it's easy for you to get the differentiation of the how photons or particles get reacted in with your PMT. And this is our set. This is the experiment cell. We have normal our distant computers and also the PMTs and also the radiation sources. In our laboratory also we are so lucky. We have neutron radiation source, we have beta radiation source, we have alpha radiation source, and also we have gamma radiation sources. So we can test this material, and also we are on black boxes, and also we have this the high energy or particle based electronics kind. So we are working with that also. This thing. So first of all, we have different modes, and we try this mode to see with the cosmic and also the gamma radiation. So as you can see, for the cosmic, each mode is capable of detecting it. But when you put radiations, that is why secondary emission is in the work. Because when you put radiation, the energy is high. Cosmic, the energy is not that high, but the flux is high. That's the difference between the cosmic radiation and the normal applied radiation, like gamma radiation. Gamma radiation, the energy is high, but the flux is easy. Like here, we have a lot of photons, any like this. So as you can see, on the cosmic radiation, all modes are working. But when you put gamma radiation, you see, the change is huge for the mode 1. You see, gamma radiation. So we are saying this our material is really sensitive for both cosmic radiation and also the gamma radiation. So we observe that our first mode is more sensitive for both cosmic and gamma radiation. So we choose this one to make neutron detection with it. So after we get this thing, our first mode is working high. So we try to integrate gadolinium. As I mentioned before, gadolinium is very interesting material because it's easy to capture neutron and also emit gamma radiation. So and neutron are very low energy and low charge particles, so it's hard to detect them. But when you integrated gadolinium oxide, it will be gadolinium in it, to be easy for us to get that gadolinium sensitivity in it. So we try different thicknesses with gadolinium, and you can see mode 1 has exhibit a very sensitive mode. So we keep on and give different. Let me show this here. As you can see here, the mode 1, the gadolinium thicknesses doesn't matter. It really doesn't matter because photo detectors, when electrons come hit the material, it doesn't matter how thick the material is, as long as this material particle can pass away from it. So the material thickness doesn't matter. The only thing is when this material interact with the gadolinium, how neutron is captured. So you can see here in our second distance. Normally, you are expecting gamma radiation to be high sensitive to any material, right? Neutron should be low. But by integrating gadolinium oxide in these detectors, it will be easy to see the neutron detectors will get high sensitive detection rate. So we are going to integrate this in and maybe in the future we will commercialize this material. So as I mentioned before, like our aim is to integrate our conventional detectors so that it will be more sensitive for high energy radiation and also low energy radiation. And it will be reliable to any radiation environment. So our future study is like to integrate this material with normal silicon-based, normal material sciences, different material oxide. So we'll try to integrate this material so that we can get easy access to our particle detections. Thank you for your attention. It's like I'm talking like no one is getting what I'm saying, or maybe you are not familiar with the topic. I'm saying like no one getting what I'm saying. Maybe they are not familiar with the field I'm talking about.
I don't know. This group are our students.
Yeah.
Maybe they are not familiar for us.
Yeah, it really is complicated because when you ask anyone now,
Yeah.
even physics, what is neutrino? They
Are
will say,
starting.
yeah, they will say, what is neutrino? Because you can't, even if for physics person to explain what is neutrino is really hard because neutrino, it doesn't have mass, very low mass, and no charge. So how can you explain we have a particle that doesn't have mass and nearly zero interaction with any matter. So it's really hard for, thank you for your attention.
Thank you. Thank you very much. The Abu Bakr name is very important for us. I will transfer you to the Beşiktaş name later. And Dr. Kılıçarslan, pardon, sorry, Kılıçkar, Dr. Kılıçkar, sorry. Correct. The presentation name is Investigation of some physical properties of CO2 films produced by ultrasonic spray pyrolysis technique. Am I correct? No, it's very complicated.
Yes, hello everyone. My name is Fatih Kılıçkan. I graduated from Atılım University in Metallurgical and Materials Department, and now I'm in a master degree student in Gazi University, also in Metallurgical and Materials Department, with Associated Professor Dr. Meryem Polat Gönüllü. We are studied on the thin films. So this presentation topic is also about thin films. Investigation of some physical properties of CO2 thin films produced by ultrasonic spray pyrolysis technique. It's our topic. There's a content. I will talk about thin films, titanium dioxide, ultrasonic spray pyrolysis, deposition as a technique. That's the general information. We will talk about the experimental part. And also we see our result and discussion. And now, as a finish, we will see a conclusion part. I will start with thin films. Firstly, I want to define this thin films is a layer that extends infinitely along any two directions, but restricted along the third direction. We want to say that when we think about the third dimension, we can extend the film on two dimensions, but we are limited on the third dimension. This limit is our thickness. Our thickness must be limited between nanometers and micrometers. So there's a comparison chart. This is not too detailed one, but we can have an idea what is that. It is more thinner than gold and aluminum foil. We can also, everybody knows what is aluminum foil, maybe not gold, but we can also everybody knows aluminum. So we need a much thinner film size as a thickness. Thin films can be categorized due to their properties. These are optical, electrical, magnetic, chemical, mechanical, and thermal. And two different main types of producing, chemical and physical. These are just a few techniques. We will focus on the chemical ones. Spray pyrolysis deposition are the producing technique in this experiment. And now about when we talk about the titanium dioxide, it has been one of the most attractive materials. There is a wide usage areas from electronic to foodstuffs. When we talk about the advantages, high photocatalytic activity, thermal stability, non-toxic, and low price, these are some advantages of that. And now there are three different phases, but anatase and rutile are the main phase. There are one Brookit phase also, but it can be obtained in special conditions. So we will focus on anatase and rutile. TO2 is a semiconductor material, and that has a wide band gap. In anatase, 302 electron volt. In rutile, there are in rutile in 3 electron volt. As a semiconducting properties, TO2 available metal for using semiconducting properties. Actually, for photocatalytic activities and maybe photovoltaics. I will talk about our technique, ultrasonic spray pyrolysis deposition. You can see a schematic illustration of USP machine. We have four main parts. One of them is heating plate. The other one is air compressor. The other one, injector of solution, which is we can use the solution to the ultrasonic nozzle. That ultrasonic nozzle, the other main part. We can, with using this part, we can setting up the flow rate, air pressure, and substrate temperature. So we can control that while we are doing our experiments. There is an experimental chart. Maybe I can say that there are 6 main steps. In the first step, firstly we use a Corning glass, which is can show good property on higher temperatures, and we should firstly clean the substrate. So clean the glass in ultrasonic bath. After we clean our glasses, we need a solution because this ultrasonic spray pyrolysis technique needs a solution. There are three chemicals: titanium isopropoxide, ethanol, and acetylacetone. Titanium isopropoxide and ethanol 1/6 ratio as a volumetric, and titanium isopropoxide and acetylacetone 1/1 ratio. We use that solution. And now, after that, we prepare our solution. Stirring, we need to stir the solution for 2 hours, about 2 hours. While this stirring happens, we should prepare our USP machine. We should put our cleaned glass on the heating plate, and we setting up the 450 degrees our substrate, so our glasses are getting heat. After that, everything is ready. Our prepared solution is sprayed on Corning glass for about 10 minutes. We use the solution. Because of the heat, we should wait inside of the machine. We shouldn't take out the glass because of some crackings. It can be cooled down inside of the machine. After we obtain the thin films, we need an annealing for better structure, better properties. We have 4 different temperatures: 6, 7, 8, and 900 degrees. All of them, all samples annealed for in this temperatures, annealed for 2 hours.
Are not minus, right?
No.
It looks, yeah, looks like
Ah,
minus.
yeah, maybe I should use a dot.
Yeah.
Yeah. These are,
It will be better.
yeah, over the zero. And after annealing, it's also cooling down slowly inside the furnace. After we, as a last step, prepared TO2 thin films are analyzed on XRD, SEM, and AFM. We will talk about. These are the our samples after annealing, 4 different temperatures. You can see actually 900 degrees as there is a different surface than the others. So we will talk about in XRD and AFM structure what is that. And I'll talk about the XRD. There are some 5 different charts. The bottom one is as deposited, so without any annealing sample. In general, we see that in the literature, generally amorphous situation without any annealing, but we see that in about 2 theta degrees, 25 degrees, there is a strong and intense peak. So this is maybe surprisingly, but it looks much good for us. When we look to the other temperatures, 6 and 700 also continue the anatase phase. When we come to the 800 degrees, there is a so little, you can see on the star, that one is rutile phase, but this is not a peak. This is just a little thing. When we see the 900 degrees, which is a milky structure, which what I show in the previous slide, we have a rutile phase in near of the anatase phase. So we can obtain a phase transformation with anatase to rutile, but we should see 2 of them in same graph, in same chart, anatase and rutile. You can see some images of NaOTO2 films. Grain boundaries and grain size can be obviously seen. For the 600 degrees, we can averagely 50 and 500 nanometers grain size. 700 is also same, but getting a little decrease the grain size. We can see much better in 8 and 900 degrees. Our grains going to the particles, and especially in 900 degrees, we have a squeezed particles on the surface. We can see on the SEM images. These are AFM images. There are 3 images in here. In 600 degrees, there are so many agglomerated points on the surface. There are also homogeneous structure, but generally we can see so much big agglomerates on the surface. When again the temperature, annealing temperature increases, our structure, our surface getting much more homogeneous. You can see the difference 800 and 600. Because of the 900 milky structure, milky and opaque structure, AFM couldn't see the surface correctly. So, but we can see the 600 to 800, our surface getting more homogeneous. As a conclusion, I said that titanium dioxide is suitable material for thin film in ultrasonic spray pyrolysis deposition technique. XRD data show that we can have anatase rutile transformation, phase transformation when we do it with ultrasonic spray pyrolysis technique using a titanium isopropoxide precursor. SEM image also we talked about our grain size getting decreased, and also AFM images are show that our surface topography in first annual temperatures our surface getting more homogeneous from the agglomerated particles. So you can see the references. So thank you for your attention. If you have a question or because of we use a Corning glass, which is not a microscope glass. It can be its straining temperature about 600 degrees. Its melting point about it must be 1000 degrees. So there is a between degrees we can look what we do. So we can obtain a better structure and better XRD data from the higher temperature. Yes. Mm-hmm.
You get the optical structure and the electrical structure at 800 degree, you get optimal. So
in 800 degree? In here?
Yeah, even my study is 800 degree, but my study is electron beam.
Electron beam, yes.
Yeah, so now I'm asking, like, is it possible you to animate above 800 degree or below 500 Celsius?
Above the 800 degree, we had also 900 degree centigrade degrees annealing. You can see the this one. See the difference on the surface. There is a milky structure. AFM couldn't take any surface morphology with a healthy surface morphology. So, but this can be also the experiment conditions. Inside of the furnace, there are some changings, melting down because of the maybe furnace location. But in generally, as I see, Corning glass can goes up to about 1000 degrees, just like that. You're welcome. Okay. Yes. Of course. Mm-hmm.
How about the start to work at the third dimension, which is the thickness of the CO2 film?
Mm-hmm. Mm-hmm.
Why it is hard to work the third dimension?
Yeah, because we have a limit. There's a comparison chart. I said that it is not too detailed one, but just having an idea. Thin film must be between nanometers and micrometers. Our thickness. We can have much more bigger thin film, but we can't have more thickness from the micrometers. For example, we can have a millimeter thin film. That one is a thick film. So we are limited on micrometer and nanometer between. You're welcome. Another? Okay.
I don't know if there are any online participants or not. Not? Okay. Okay, this was the last presentation day. Thank you for your participation in our conference. Thanks.